So, hello. So we'll start with the introduction. Welcome to this video where I will explain my deep learning project for uh, food quality detention. So in this project, I used a data set for uh, rotten classification, and I'm using ResNet 18 model to run my project. So my goal is to build a model that can automatically detect the quality and the quality of the food, that is vegetables or fruits. So in these, this is where we are importing the libraries. So these libraries are used together in a food quality detention project, like to handle data, process images, and build AI models, evaluate results. So we can see libraries like NumPy, Pandas, OS, which help manage image data and labels. And we also have PyTorch, and its models are used to build, train, and evaluate deep learning models that can also classify like food is fresh or it's spoiled or what. So these are the libraries we are using. And next we are loading our data set. So this code right here is used to load and organize the image what we have to check the food quality. So the we have a function here uh, that is load data, which collects like images, files paths, and the type of fruit it is, and it shows 0 and 1, like whether it is fresh or not. 0 means like it is not fresh, it's spoiled, and 1 means it is fresh, the quality is good. So all this information is stored in a table, which is data frame, where we are using pandas, which makes it easy to work later during training. So finally, it prints out the different fruit types in the training and testing data. So in this code right here, it removes the like unwanted fruits categories, and fixing also it fixes the spelling errors and all. So after those things, we can see the output here, like unnecessary uh, data like bitter gourd and okra, those have been removed. And we'll next go to data distribution. So here we are training and testing data sets into one single data sets called df using pd dot concat. So here we can see like the kind of fruits we have, and 0 means it is fresh, and how many fresh bananas we have. And then there is another, we have section banana. 1 means um, 1 means fresh, 0 means like not, it's spoiled. So we can see there are many fruits and vegetables where we have the fresh, whether it is fresh or not, and the count how many it has. So we can also see a graph here. So these are the vegetables and fruit. We can see like 0 here, that fruit, and the count, like how many are there and how many are fresh and how many are not fresh. So after that, we'll move on to the next part. So this part code is visualize and understand the distribution of this code creates a new balanced data set by making sure each fruit type has the same number of samples. So here they have divided, the minimum they have taken is 800 count, and d type int 64. And so all these here, so yeah, so this image here is a bar plot creating using Seaborn, displaying the count of different fruits categorized by their freshness. The x-axis lists fruits like orange, banana, tomato, and all. So while y-axis shows the count of each. So and not fresh equal to 0 fruits. So and we'll move on to the next. Here we'll see the training and validation split. 15% of the data was used for validation here. So this code splits the balanced data set into two parts. One is for training the model and one for validating it. About 15% of the data is kept aside for validation to check how well the model learns to on unseen data, and the other one, like, the make sure that the different fruit types are evenly represented in both training and validation sets. So then this bar plot visualizes the distribution of fruit based on their labels. The x-axis represents numerical fruit labels, while y-axis shows the count of each fruit. So the bars are color coded to distinguish between this is fresh or not fresh. Uh, so, for example, the fruit label 0 has the highest count, with most being fresh, while label this 5 has fewer fruits and a mix of fresh and non-fresh. So this shows the relationship between fruit types and their freshness in the data set. Uh, and this bar plot shows the count of different fruits in validation set. The bar use a blue gradient palette to distinguish between the fresh from non-fresh fruits. So, and right here we have, so this code shows the images are loaded from the file path that is stored in the dataset right here. um, uh, it resized for real visualization and arranged in 9 row by 3 layout. So these are the images. Each image is labeled with its class name, like you can see banana, capsicum, using inverse transformation. The plot helps visually expect the variety and appearance of fruits in different classes. uh, and if we move on to the next part, so here we'll come to the main part, like building the data set. So the here the batch size is 64, meaning the model will process 64 images at a time during training. Two dat so These data sets are wrapped in PyTorch data loaders, so to load the data efficiently in batches and shuffle the training data for better learning. So the dull statement, they then there here it what does it does that it frees up the memory by deleting the this temporary variables. So ResNet. So this code loads pre-trained deep learning model called ResNet 18, and which commonly like here, yeah. So we'll come to here model architecture. So this is what it does is this code loads a predefined deep learning model called ResNet 18. which is like commonly used for image classification tasks because it's powerful and also it is efficient. The model weights are like loaded from the saved file, so it already knows how to recognize features from images. So we have model.eval here. It is like prepared for testing and making predictions rather than like training. This way you can use like why I used this is it's strong and ready-made model to help like detect food quality without like uh, me training a model from the scratch. So this statement confirms that this model loaded successfully here. And these whole like this is my ResNet model path. So this code defines a custom deep learning model built on top of pre-trained ResNet 18 to classify like both the type of fruits and its both the type of fruits and its freshness. It freezes most of the ResNet layers to keep like learned features stable. So this over it uses different optimizers for a different part of the network and tracks accuracy of both tasks. The here the train model function runs the training and validation loops. So this setup helps the model learn efficiently and effectively while leveraging pre-trained knowledge. And so here we have the training completed, and here we have trained our model, and I have run 15 epoch, and you can see the uh, accuracy is so the final accuracy which I've got is 98.57, and it shows that training completed. So next we'll come to model prediction and visualization. So the above this part the accuracy is like uh, the value loss the see you can see value freshness accuracy is equal to 98.57. And next we'll go to model prediction and visualization. So right here this visualization summarizes that the performance of a machine learning model is trained to classify fruits and their freshness. uh, So the confusion matrix shows that near perfect accuracy for fruit identification, um, like banana, capsicum with like um, incorrect prediction each, and high accuracy for freshness detection. Um, so so here this uh, where is it? So the precision recall curve demonstrate that the strong performance across all fruit classes, while the ROC curve for freshness classification and shows an excellent accuracy of like 0.98%. Finally, the F1 score bar charts. Yeah, so this chart highlights the consistent performance with like all fruits classes scoring above like 0.98 and freshness detection like 0.97. Overall, the model excels in both tasks and minimal errors. So next we are saving the model. So this is all for saving the model, and after that, like after this, we will be able to see the model dot path in here in output. So we can see like this output displays a grid of like 12 images, fruits like banana, tomato, and all, and whether it is its status is fresh or not. So we have can also see that predicted and freshness equal to 95 by even the percentage they have given, like how the quality has been showed here. Um, so after that, while we click on this after that, once we get the model.path, we'll test our images. Like we'll start with the orange. If I just copy paste this here and run it, and it shows that orange is the fruit is orange and the quality is fresh. And we'll next move on to the next one. So we can see the photo is that the photo is of spoiled orange, and it is also showing that the fruit is orange and it is spoiled. And banana, will move on to the next one, which is a fresh banana, and we'll give the path here. So I've given a path and I'll run my model. So it is saying the fruit is banana and the quality of it is fresh, and we'll have a spoiled banana. Uh, so, so we'll run here, and it is showing that the banana has been spoiled. And same goes for the cucumber, and the last one, that the freshness will check. I'll give the link path. So and we can see that the fruit is a cucumber, and the freshness of this fruit is quality of this fruit is that it is fresh. That is what it is showing here. So this is all about my project, like the quality of the food, whether it is fresh or not. So Rasnat 18 I have chosen here because it is efficient and effective also, and it's like I don't need to train the model from scratch, and so it's very helpful and easy to run. So we'll come to the research papers that I have come across for this project. is like, can a single model effectively access quality across multiple food categories? Uh, so, so the answer is yes. A single model can effectively access quality across multiple food categories. Like if it is trained on a balanced and diverse data set, uh, like one can build using fruit and fresh labels. So the backbone ResNet 18 and the dual output heads, like one for fruit classification and one for freshness. So these are the example of multitask learning, so which will allows the model to learn shared visual features while specializing in each task. This model achieved high accuracy on both fruit type and quality, proving that it is feasible. So the next uh, question is, how does combining traditional image features with the deep learning improve performance? So these are the in this thing, like we do not explicitly use traditional features like texture or color, but our data augmentation and ResNet 18 architecture capture the low level features and also the high level semantics. So if traditional features were added, um, they could complement deep features. So especially when the training data is limited, or when the fruit is damaged is subtle. So this hybrid approach often improves our generability. Next question is like, what is the minimum image resolution required for reliable quality assessment? So our model resizes images to like 224 into 224 pixels, so which is standard for our model ResNet, and generally sufficient for fruit classification and also quality retention. So, and the fourth question is, can we develop a quality scoring system uh, that that correlates with consumer perception? So the answer I would say is yes, because the current binary, that fresh versus spoiled labeling, simplifies us that the quality. To build a system that aligns the consumer perception, we would also need more labels and user surveys and possible model predicting a quality score rather than a class. And the fifth question is, how to make the system robust to varying lighting condition in a real world settings. So, real world lighting variation is a key challenge. We addressed this partly through data augmentation. So, by the use of photometric augmentations like color, brightness, contrast changes during training. So, this this model this helps the like these all things like um using training and applying all these helps our model to generalize better and not overfit to studio lit training images. So this is all about a research question which I have mentioned in my proposal, and this is all about my project. I conclude my project here. So yeah, thank you.